Greetings, everyone. I finally wanted to get to our makeup lectures, and I apologize once again for it taking some time. But the first concept that I wanted to present is, obviously we talked about integer programming, but what I wanted to do was focus on some of the calculations that are going on behind the scenes, right? What we found is that it's quite easy to add a integer constraint. Solver makes it pretty intuitive. And we talked about obviously different types of IP models. Obviously we have the binary method. We have the mixed integer method, where we have one or more variables that are continuous and one or more are integer based. And then we have what's called the pure integer, where essentially it is what it sounds like. All solutions have to be in integer format. So we have conceptually, we have a general understanding of what we're doing, and we were able to apply this type of method in a variety of different applications. But what I want to talk about more is, obviously, as we create larger models, we introduce a lot more complexity, right? We talked about implicit enumeration and what are all the possible combinations and solutions and how that is inefficient. So instead of having to do implicit enumeration for these IP problems, what we can do is actually use this method, which actually Solver is using behind the scenes, which is called branch and bound. Okay, and in a nutshell, excuse me, I just got an email here, but in a nutshell, what we're doing is we are creating groups or subsets within all possible integer solutions, and I'll just get into that here momentarily. Once again, this is talking about the fact that if we were to have several changing variables or decision variables in our model, and in this case it was a binary 0, 1, I have 100 different changing cells. Well, as you guys can see here, this exponential value, the number of solutions or combinations to verify would take quite a bit of time. All right, and obviously technology has helped to kind of alleviate that issue. But models can get much more complex, have many levels, thousands of variables, so it can be inefficient and impractical. So when we talk about using this branching method, branch and bound method, essentially what Solver is trying to do is identify all possible, I shouldn't say all possible, but all feasible integer solutions. And what it does is it kind of like categorizes them, creates subsets or branches of these possible solutions, integer solutions for your problem. And then what it does is, with each one of these branches, it's kind of like a decision tree. With each one of these branches, what it does is it finds the best solution, the best feasible solution, right? And we call that the incumbent solution, which you see right here. So whatever the best possible solution is, we call that the incumbent. And the beauty about branching and then bounding is to find a upper and lower bound to which you can identify that optimal solution. And obviously, we need to compare it to something, right? We need to compare our optimal solution for our IP problem to something else. And that something else is using what's called LP relaxation. Okay, LP relaxation, I'll get to it in another slide, essentially is saying that I am removing the IP constraint from my problem. I'm solving it as a straight up linear programming problem using the simplex method. I arrive at an optimal solution. Okay, and as we know, when we use LP, when we use the LP and we use simplex and we remove that IP constraint, we know that that is surely the optimal solution, right? And if I was to introduce the IP constraint, the value would be less than or equal to that optimal value as calculated before using the simplex without the IP constraint. So we call that LP relaxation, where we first solve it without using the IP constraint. And let me just jump to this slide here. So we call that LP relaxation, and the way that we set that up in Solver is, let me just go back one slide here, is if we were to click on options in Solver and go to all methods, we have something here called, I don't know if you guys can make that out, but it's called integer optimality percentage. So this is basically saying, what is the bound, okay? What's the upper bound? Or in other words, how close do you want to get to your optimal solution using LP relaxation, okay? So in this case, I'm saying I want to get to within 5% of that optimal solution as found using LP relaxation. Now, the basic question is, okay, why use 5% or why use 3%? Why not just use 0%? So let me just go ahead and skip over to this slide here. Now, obviously we could run a 0% tolerance, as we call it. We also call it solver tolerance, or integer optimality at 0%. But the problem is, especially with larger problems, when we introduce many decision variables, many constraints, it becomes quite difficult to find, okay? And so this is why we use this tolerance level of either 3% or in this case 5%, so that we get as close as possible to the optimal solution using LP relaxation. Okay, and as you know, we talked about many different examples. We did capital budgeting, we did fixed cost methods, advertising methods. So this is surely a powerful tool using IP, but really what I wanted to do in this brief lecture is tell you what's going on behind the scenes in Solver specifically. And so as a quick assignment, what I would like you guys to do is talk about LP relaxation. Sorry, I got another email here. Just talk to me, what is LP relaxation? What does it mean to, basically, let me just go back here. So like I say, integer optimality 5%, just recap and tell me what exactly is that trying to do. Okay, so if you can summarize that in 2 or 3 sentences, I will publish an assignment on Canvas here tonight, so please be sure to get that one done. Okay, so this concludes my first lecture, our first makeup lecture. Thank you for the time, and see you tomorrow.